Okay, today it's a combination of two lessons today. We're not doing every part of both, but we're doing some of both. And these, because they kind of go together. In the 1.6, we look at all the different parent functions or common functions, whatever you want to call them. And then in 1.7, we show how do you shift them around. Yeah? How do you go left, right, up, down, flip, stretch, shrink, all that kind of stuff. I would say that probably the hardest things that you're going to find in here, though, are going to come out of the first section, and it'll seem like it's not either one of those. One of them is, how do you come up with the equation of a line if you know 2 points? 2 points in function notation. And how do you graph a piecewise function? Right? Those two are probably the ones, you know, that you'll struggle a little bit with. The linear one you shouldn't, but would seem to. The piecewise defined function, we usually have a trouble, you know, kind of just grasping the whole concept of a piecewise function. Okay. These will go up at the end too, if you want to. Right? These are the common functions. The parent. Okay, they're calling the parent functions. The old version of this textbook used to call them common functions, like the Algebra 2 book did. The new version of the book, they're calling them the same thing, parent functions. And you could see that the first two are actually linear and in straight lines. A constant function is a horizontal line. The identity function is f of x equals x or y equals x, meaning 0, 0, 1, 1, 2, 2, and every point in between. Right? Whatever is the x coordinate, that's what the y coordinate is. And again, those are ones that we don't think of as much. We're pretty well versed in absolute value, the v. We've seen that all the time. The square root function is a good one to show a lot of these things with. Quadratic, which in the book sometimes they're calling this a squaring function. I wish they'd just say quadratic, but they don't. Right, this is a cubic function. They're calling this a reciprocal function. We call that the inverse variation. It's 1 over x, or k over x, or whatever. They're calling it 1 over x. But we called it last year, we called it k over x, where k could be any constant, including 1. And this one is one you might have seen, you might not have. It's kind of useful sometimes to show concepts of domain and range and continuity and things like that, even though it does look kind of made up. And they're calling that the greatest integer function. But it's also sometimes referred to as a step function, right? Because it looks like a bunch of steps. Okay. And now, these are all on the inside cover of your book, or they're summarized at the end of the section. I copied it from the end of the section. But if you just go to the back cover of the book and look, you've got all of these and more. Right? But these are the ones they're presenting now. Okay. So the first thing, which again will seem like it's a little disconnected from the rest, it is their first example, and honestly I think it's useful. Right? Write a linear function, where by linear we mean something like mx plus b. If you're given these 2 points, f of -2 is 6, f of 4 equals -9. Do you see how when they give you this function notation like this, they're really just giving you 2 points? What are the 2 points? Yeah, the x is the -2, right? -2, the y is the 6. The x is the 4. The y is the -9. So given 2 points, how do you write the equation of a line? Let's say that we want to come up with, we're going to try to do y equals mx plus b, but in order to get there, we're going to start with this one. Y minus y1 equals m times x minus x1. That's called the point slope. In order to use the point slope formula, you need 1 point and the slope. That's why it's called point slope. Okay. If you don't have the slope, but you have 2 points, what else could you do? Calculate the slope, right? If you're given 2 points, then that just means find the slope first. So let's see, our slope will be, and then you have to do the y2 minus y1 over x2 minus x1. Remember, it doesn't matter the order that you do that, just as long as you're consistent, right? If you want to say 6 minus negative 9 in the numerator, then you got to do negative 2 minus 4 in the denominator. Right? If you do negative 9 minus 6 in the numerator, then you do 4 minus negative 2 in the denominator. Just be consistent. How about I'm going to do negative 9 minus 6 over 4 minus negative 2, which is negative 15 divided by 6. And then I can simplify that. Right? Common factor of 3, negative 5 halves. Okay. So now we know the slope, and we know 2 points. How do I use that equation? Plug them in, right? Going to plug in the slope, which we calculated. Which point are you going to use? It doesn't matter, right? Either one. Does it make any difference? Looks like the numbers are smaller with negative 2, 6. How about if I use that? I'm going to call that one my x1, y1. So y minus 6 equals negative 5 halves x minus negative 2. Y minus 6 equals negative 5 halves x plus 2. Now I'm going to put it into slope-intercept form. Solve for y. Y minus 6 equals negative 5 halves x. And what do you get if you multiply negative 5 halves times 2? Minus, oops, sorry, x. And that'll be minus 5. And then the last step, add 6. Y equals negative 5 halves x plus 1. So what does the 1 represent? The y-intercept, right? And the negative 5 halves is the slope. That's slope-intercept form. That was point-slope form. The question? Okay, example 3, coming from the same section, is graph a piecewise function. What's that? I didn't do it. Okay. I don't do every example. If you want to go look at example 2, knock yourself out. Okay, so a piecewise function, again, is a function that's defined differently for different parts of the domain. The domain is given by these statements here, right? These are the domains. So we're going to use, when x is less than or equal to negative 4, we're going to use this to define the y values. When x is greater than negative 4, you're going to use this to define the y values. So it's going to change. Let me do this. Where's the dashed line? And it's going to change right here. should have made that bigger, but so it'll be a different graph to the left of that than it is to the right. Now, I put both of them in my calculator, right? This is the negative 1/2 x minus 6, and these are the, for the x values of -7, -6, -5, -4, these are the y values, right? And then on the next line, I put in the x plus 5. So I'm just going to plot a few points and connect them up. So let's see, -7, -2.5, 1, 2, 3, about right there. -6, -3. -5, -3.5. -4, -4. Okay, the next, for -3, I use 2. -2 is 3. -1 is 4. Is that enough lines dots to see where a graph is? Right? So now notice that the or equal to was with the first. So definitely we want to have that was going to be a closed circle for the -4. And the graph would look something like this. Okay, for this one, then if I connect the lines or connect the dots, it's got to go all the way up to that line, right? It starts when x is greater than -4, but it does not include -4. So I do an open circle at x equals -4, and then it goes off like that. That's a piecewise function. But you don't want to draw like two lines in the same part of the graph. Like you shouldn't have this line extending over here, so then there would be two lines in the same part of the domain. It's always going to go up to a point. You've got one line. After that point, it's a different line. And they're not necessarily connected. Sometimes they are. Sometimes they're not. Now, we could have graphed these by using some, how do you graph straight lines? Y-intercept is -6. Slope is -1/2. 1, 2, 3, 4, 5, 6. Slope is -1/2. That would have been something like that. Y-intercept is 5, slope is 1, which would give us this. You then just make sure that you only draw one line at a time. Erase the part that's not included. Or just plot some points. But make sure you don't draw more than one line for the same x values. I mean, one thing to imagine, what if I did that? What if I continued this line over here? Would it be a function? It wouldn't be a function anymore, right? So by definition, it's a function. So you can't have more than one y value for each x value. Yes, sir.
So each is plug that into the calculator, and we plug the calculator into the graph.
You could just use those to plot points, and then. I mean, you know what? I'm going to assign you my class at calculators for a while, just use it in class. And I can show you actually how you can do this in the calculator. For right now, I don't want everybody to go up and get them this moment, but I'll show you. Yeah, you could do this in the calculator, and I'll show you. You go like this. If you want to do a piecewise graph in the calculator, go like this. This first one, -1/2 x minus 6. And we want that to be good for x less than or equal to -4. Okay, first I put this, but I put it in parentheses. So make it parentheses, negative, I'm going to say -0.5x minus 6, end parentheses, and then do a divide, right? Make it a divide symbol like that. And then put in the domain statement. In this case, it was less than or equal to -4, right? X. Now, where do you find the less than or equal to symbol? Math, above the math, right? Second math less than or equal to was the 6. And now I put in my -4. Okay. And now I go down to the next line, and I'm going to put in x plus 5, x greater than -4. Parentheses, x plus 5 divided by x greater, second math, greater is 3. Oh, that was wrong. Greater than -4. Does that look good? And then when I hit the graph, zoom 6, it draws just that function where you wanted it to, right? And when you look in the table of values, that's what I did there. I just grabbed those. Right? It only gives you the ones that are appropriate for that part of the domain. So yeah, you could have it do it. The main thing is the understanding of what it is. A piecewise function. Okay, that gets us to the next section, which is about all the transformations. And honestly, we kind of beat this to death in Algebra 2. I mean, it's a fairly big thing. Every kind of function we learned that you can shift it around by adding, subtracting, multiplying, dividing, putting in negatives, all kinds of stuff. And to me, the absolute value function is a good one to show because it's so clean. You can really see what's going on with an absolute value function. We know what the parent function of absolute value looks like, right? It looks like, I'm going to make it, it's a V. Right, oh, what happened there? Undo. It's a V that looks like this. Something like that. So what we're trying to figure out is what happens to the V when you add or subtract inside the function, right? So if f of x is the absolute value of x, we're going to define g of x is f of x minus 2, right? How do you find f of x minus 2? You put x minus 2 in the place of x. Well, notice on this graph, f of 0 is 0, right? Which means that's why you're on the x-axis, right at the origin. When x is 0, y is 0. But what value are you going to plug in to this, the absolute value of x minus 2, so that what's inside the absolute value equals 0? Positive 2, right? That means that if you want the point of the V, the place where it touches the x-axis, you're going to have to go to x equals positive 2. So let me change that to blue. So when I subtract 2 inside, it's actually moving the point of the V to the right. I mean, we always have this thing about, the opposite sense of it, that you think it's minus, so why doesn't that go to the left? That's why it doesn't go to the left. Now, we're trying to do, what would we substitute in here so that we are taking the absolute value of 0? Positive 2. Right? That's why when you say x minus 2, it goes to the right. Now, it's a little more straightforward. Here's h of x is f of x, and the plus 2 comes after the function, which means the absolute value of x plus 2. What's the effect of the plus 2 there? Yeah, it's going to take every y value and add 2 to it. So it's going to move the whole graph up 2. Right? So that would be like this. So in summary, right, these are what we call the rigid transformations. I mean, it's going to take that shape, rigid shape, right? It's not going to bend it or any other way. Just taking that shape and moving it around. That's a non-rigid, that's a rigid transformation, right? If you add or subtract after the function, plus means up, minus means down. If you add or subtract inside the function, minus means right, plus means left, right? And we did absolute value, but it would work the same no matter what the function is. We're good. Bryce, Morgan, okay. Allie, good? Okay. So as an example, if we try to move the function f of x equals x to the third, what would be the effect of adding 5 after the function? It's going to go up 5. So let me see, am I in blue? So this is going to be up 5. So usually the best way to do that is just take some fixed points that you know. I did graph like the -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. So I could just move those points up 5, right? Here's a 1, 2, 3, 4, 5, 6, 7, 8. So it goes up 5. 1, 2, 3, 4, 5. There's a point. 1, 2, 3, 4, 5. There's a point. 1, 2, 3, 4, 5. There's a point, and then that one we can't see. So graph. Just take some fixed points, draw them up 5, connect the dots. Okay. You can pick any point you want. There's usually some that are a little easier to identify. Okay, how about this one? I'm going to try to make that fatter. What are the shifts that are going on here? What's that -3 inside the... Oh, you know what? Okay, that should have been... That was wrong. What's the -3 doing? Right and up. So if I take just a few fixed points, like this point down here, if I go right 3 and up 2, right 3, up 2, I'll take my -1, -1, right 3, up 2, take 0, 0, right 3, up 2, okay, 1, 1, right 3, up 2, and then the last point's going to be way up here somewhere. You can still kind of see the shape, right? This is the shape we started with. That's kind of the shape we're ending with. Everybody remember this stuff pretty well? Okay. Okay. Reflections. So I'm using the square root function to show this one. And the square root function, I'm just going to draw kind of an idealized version of it here. So if it's not exactly the thing, we know it starts at 0, 0, and it kind of goes off like that. What's the effect of sticking a minus in front of it? Flips it where? It flips it across the x-axis, right? I think in this book they call it, it's a reflection in the x-axis. That's the way they say it, reflection in x-axis. which means it will go like this. And almost everybody's familiar with that, right? But the one we don't do as much is what happens when you actually put the minus inside. That's the one which is a flip across the y-axis. I mean, think of it like this. The square root, you can only take the square root of a positive number. When you stick a negative in front of the x, that means the x's better be negative, so when you put the minus in front, they're positive. So now our function is going to go, our graph is going to go from here to here. Right, so that's the one which is a flip across the x-axis. That's the one that's a flip across the y-axis. Right. So reflection in y-axis. So why would I have not used absolute value to make this example? You wouldn't see the difference, right? If you flip a v across the y-axis, it's the same v. So I was looking for a function that it was a clear, that you were going side to side. It was clear that you were doing here. It was clear what you're doing here. We'll call those reflections. Okay, so graph using the transformations of the absolute value of x. So meaning we're going to start here. Let me draw in a couple points. Right, so the absolute value of x would have points like this. There, 2, 4 would be there. So it looks like this. Something like that. So what's going on with the blue, g of x? What's the minus 1 doing? Right 1. And what is the minus in front doing? Reflecting across the x-axis. Right? So if you took this graph and moved it to the right 1, it would be here, right? But now we need it to go here. So that is right and flip x-axis. So when we get problems like this, the point is not to like do a table of values. The point is to show that you understand that we're just transforming the parent function. That's why these don't have to be like point for point exact. Just they got to show the right transformation. What's going on in this one? And move to the right one. So he's saying it's moved across the y-axis and to the right one. Close. It's going to be like this, right? This is like saying negative x plus 1. So we're taking the function which would have been the square root of x plus 1 and then flipping it across the y-axis. Well, what would it have been if it was the square root of x plus 1? That would have been that shifted which way? It would have gone this way, right? It would have been here. Okay? But now we're going to reflect that because of the minus, and it's going to go like that. So, if it would have been here, now it's got to be here. Right, so this is left and flip across the y-axis. Let's see now. So if I put in 1, that doesn't seem right. That's not right. That's not right. How can you see that's not right? And I make this mistake sometimes. Well, just test a point, right? Which point did I just say is on this graph? 1, 0. What do you get when you plug in 1 here? You get 2, negative the square root of negative 2. That ain't going to work. It's actually not, it's the flip is across that line. It's a reflection in this direction, but it's not on the y-axis. It's on that line. Let me take back. Watch. Right. So we said if it was like that and you flipped it, it would be like that. Now let's make sure we've got the right points. When I put in negative 1, negative 1 plus 1 is 0. Square root of 0 is 0. So that's starting at the right place. So I made a mistake there. Is that, it's like, is it really flipping across the y-axis or is it flipping in that direction? They still call that in the book. They're still calling that a reflection in the y-axis. Right? So we've got our rigid transformations and we got our reflections. And now we got our non-rigid transformations, meaning these are not going to preserve the shape of the graph. So I'm using, as the best example I can think of here, the absolute value of x. It's pretty clear what's going on here. The non-rigid transformations are when you multiply by a number, multiply the function by a number. In this case, I'm multiplying it by 2 and by 1/2. Okay. The first time when I multiply it times 2, notice what happens to all of the y values. Right? These are our x values from negative 2 to 2, negative 2, negative 1, 0, 1, 2. For f of x, that's what's already graphed, 2, 1, 0, 1, 2. That's the v. What happens when I multiply all those y values by 2? It becomes 4, 2, 0, 2, 4. So the graph, I should do this. Graph there. Make it blue. Make it like that. Now the graph is going from here to, right, it's going up faster. Right? 0, 0, 1, 2, 2, 4. And the same thing on the opposite side. It should be going like that. So what did it do by multiplying by 2? It made it go up faster. That's called a vertical stretch. Sir? Okay. What's that? Are you talking about that one? We needed that negative to be, in front of some whole thing, right? I mean, here it's distributed on 2 different terms. So I needed to pull it out to see what kind of reflection is going on. So in order to make that minus in front of the whole argument there, I factored out a negative 1. Okay. Okay, now what's going to happen when we multiply by 1/2 instead of 2? That means all the y values will be half the y values that we started with, right? 2 becomes a 1, 1 becomes a 1/2. So here's our new, that will go like that, and like. So when you multiply by a number which is bigger than 1, it's going to stretch the graph. It's going to make it go up faster. That's what's going on here, right? So this is a vertical stretch. when you multiply by a number which is less than 1, that's going to make the graph go up slower. That's a vertical shrink, right? The graph here, vertical shrink. And that's called a non-rigid transformation because it did change the shape of the graph, right? The V had this shape. Now it's got this shape. It's a little bit tighter, right? And this one's a little bit wider. Jordan? Okay. What's that? So that's what we did, right? First we looked at the linear and piecewise defined functions. That was in the first section, right? And we looked at the graphs of all the common functions, at least the ones we're using now, right? Which you have in that section, you have in the back cover of your book. And then we reviewed basically, how is it that we shift the graph up, down, left, right, reflections across the X, reflections across the Y, and the non-rigid stretches and shrinks. So there's a little bit of homework there and there. Now, I'm going to